So, welcome back. You probably have gone through 7 hours of video lectures on the theory of estimation. Must have been a bit heavy, but as I said it was inevitable, and hopefully the illustrations in R lightened up the discussions for you. And as I promised in the last video lecture, we are now getting into the world of applications. Of course, there are numerous applications of estimation theory, innumerable in fact, but we will look at 3 broad areas as I had outlined. The first one is on hypothesis testing, which is the topic of this lecture. The second one will be on fitting distributions, and the third one being linear regression. We will spend most of the time on linear regression in this 7 hours of application. Hypothesis testing is something that you would have seen in module 1 in the course on introduction to probability and statistics. So, I will keep this lecture quite crisp, but the main tool that we will use for hypothesis testing is a confidence interval construction. So, if you are not if you have not fully understood the concept of confidence interval from the previous lecture, I would recommend that you go back, spend time, ruminate on this concept and then come back, right. Although there are many other ways of doing the hypothesis testing, I would prefer the confidence interval approach as far as this course is concerned. So, let us get straight to the discussion and review some of the concepts of hypothesis testing. Let us spend a few minutes and probably this will be also a bit light on the discussion since you are familiar with this topic. So, what is essentially hypothesis testing? It is essentially testing of a postulate. The analyst who has the data makes a postulate, and that postulate could be typically on the on a parameter of a model, or it could be on the parameter of a probability distribution or anything else. In fact, a true experimentalist would first postulate the hypothesis, design the experiment such that maximum information is gathered, and then conduct the hypothesis test using the data as evidence. And the basic idea is to see if the data supports a particular postulate or otherwise, and we will go through a few examples to make these things very clear. So, there are many examples that you can actually look at. I have just listed 4 of them. Some of them are relevant to what we are going to see later on. A very common postulate that you will see in hypothesis testing is that the mean of a random variable is some test value mu naught as against being different. Now, this is really a ubiquitous thing that you will see, and as far as the applications of this hypothesis testing is concerned, there is no field in which you cannot see this, or in which you will not see this. These examples are just representatives of the generic ones that you will see in applications. For example, the mean of a random variable, this mean could be for example, average marks or the average salary, average weight or the average population that you will see. So many things, average reviews in for a film and so on. So, whatever that you can think of an average, you can set up a hypothesis test of the first example. The second example draws from linear regression, where typically not just linear regression, but modeling, where we have obviously parameters in a model and we want to ask the question whether the parameter has been unnecessarily included in the model, typically the case of overfitting. And in linear regression, for example, you can ask the question, was it necessary to fit an intercept term, or is the slope truly different from 0, and so on. So, you will see in every modeling exercise this kind of a hypothesis test. The third example is more specific, where we are looking at comparing 2 training methods. So, that is the difference between the first 2 examples and the third one, where we are comparing 2 different scenarios. In the first 2, we are comparing against some postulated value, that for example, in the mean of a random variable we are asking whether the mean is mu naught, whereas here we are comparing 2 different methods. You can say we are comparing 2 different populations, one that comes out of training method A, the other comes out of training method B, and we want to ask if these training methods are different in the sense that they generated two different populations. What do we mean by two different populations? Well, you can think of the difference, for example, between the scores that they score on a particular exam. So, you train one population using training method A, you train another population using training method B, and conduct the same exam on both and see which one is more effective, and the effectiveness can be in terms of the average scores. So, this is a very common thing that you want to ask, right. It could be also, for example, in something else, maybe you are treating two crops, maybe one crop with two different fertilizers. Of course, the point is once you treat or once you train, you cannot undo. So, you will have to take two different samples and then see if it made a difference and so on. So, the third example belongs to the category of hypothesis test, where you are comparing two different populations. It could be comparing means, could be comparing variability and so on. The fourth one is more from social sciences, you can say, or law, where a person is presented in the court because the person has been charged with some it could be a crime or whatever, and the judge is looking at this hypothesis test, where the null hypothesis, the defendant is not guilty, against the alternative that the defendant is guilty. Notice that we do not test innocence, we are only testing for not guilty and guilty. Innocence is very tough to test. In all of this, you should see something common. We keep using as against, right. So, we have as against here, as against and so on. In the language of hypothesis, essentially you have two hypotheses, one which is null, which is a status quo default that you would like to believe when data is not given to you, right. For example, in the fourth one, you would like to believe when the person is not framed with any charge and no evidence is provided, you would like to believe that the person, this individual, is not guilty, and that is what should be the default for, if the country is doing well, then that should be the status quo of any citizen. That we call as a null hypothesis, and what we are testing against is the alternative, all right. Typically, in fact not typically, in principle, together the null and alternate span all possibilities. When you put them together, they span all possibilities. We will talk about that soon. So, you can now, I encourage you to think of a couple of examples at least more for hypothesis testing, and this, remember, it need not be on the averages, it could be on variabilities and so on. All right. So, how do we actually conduct hypothesis test? We'll come to this, but let me actually make a very important point here. We will come back to the procedure for hypothesis testing. No hypothesis test can result in a perfect decision. See, essentially hypothesis testing is a decision making process, where you are partitioning the possibilities into two parts, a null and an alternate, right. And the general decision that is given after the end of a hypothesis test is that the null is not rejected, as against the null is rejected. We never say the null holds, it is very difficult to do that. So, typically we say reject the null hypothesis, typically we denote null with H naught, or fail to reject or do not reject. These are the two outcomes that stem out of a hypothesis test or the decision making process. And the statement that I have circled here says, whatever decision you come up with at the end of your test is not foolproof. It is going to be erroneous, but we want to minimize that errors, and typically in any hypothesis test you will have to specify at what level of error you are conducting this hypothesis test, so that it is clear to the readership or to everyone that you are aware there is an error associated with the test, and you are also specifying how much error you have made on the average. It is a probabilistic thing. Okay. So, we will come back to the procedure, but let us talk about the possibilities of null and alternate and so on. As I said, there are two two hypotheses that are usually there in a hypothesis test. One is the null hypothesis H naught and the other is the alternate hypothesis denoted by H A, H subscript A. And since we are looking at binary possibilities 1 0 kind of thing, there can be only 4 combinations, right. So, in this table I have listed those 4 combinations along the in fact, if you go across the columns where the decision is given and the rows carry the truth in true situation. So, let us look at this possibility here. For some scenario H naught is true, that means the null hypothesis holds. For example, in a court of law the defendant, the person is not guilty and you fail to reject H naught, which means you uphold in some sense loosely said, then you made a correct decision, okay. The judge has made a correct decision. On the other hand, if you reject H naught, that means now you the judge proclaims that enough evidence has been provided to prove the accused as guilty, then you reject H naught, and but the truth is that the accused is not guilty, therefore, there is an error that is associated with this, it is wrong, right, it is false. That is an error and the probability of making that error is called a type 1 error. Simply said, H naught is true and is being rejected, the probability of making such a mistake is called type 1 error, typically denoted by alpha. And this is somewhat cast in stone, you will see that in almost every statistical textbook alpha is the symbol carved in stone for significance level, you are not supposed to change that and so on. I am just joking, but typically that will be the case. So, naturally the probability of making the correct decision is 1 minus alpha. Now, the third scenario, so we have discussed the 2 scenarios corresponding to the first row and the 2 decisions. The other scenario is that the alternative hypothesis is true. So, going back to our court example, the person is indeed guilty, but the person has been acquitted by the court and now that means you have failed to reject H naught, obviously that is an error and the probability of making such an error is type 2, it is called type 2 error. Remember, it is not error made at one instance, it is a probability, that means of if you take all such possible scenarios, the probability of making such a mistake is what is type 2 error and this error is denoted by beta. Finally, if the person is guilty and the judge has indeed or the court has indeed found this person guilty, then the court has made a correct decision, that is correct, and obviously if beta is the probability of the type 2 error, then 1 minus beta is a probability of making this correct decision. Typically this 1 minus beta is called the power of a test, alright, and we say that the power of a test is what it indicates how good the hypothesis test or how effective it is. We are not going to go in that direction. In fact, I should mention that either you go back and listen to the lectures on hypothesis testing in module 1 or you can watch a 12-hour video lecture kind of a video course on hypothesis testing that is available on the NPTEL website. I taught that 12-hour course. So, you may be interested in that where more details on this hypothesis testing is given. Alright. So, hopefully you understood the 4 different scenarios and that alpha which we usually find in textbooks as called a significance level. So, typical hypothesis test statement in many textbooks would be as follows: given this data conduct a hypothesis test with the following null at a significance level alpha. That significance level always remains a mystery to the beginners, what is the significance level, and hopefully now that the mystery is unraveled for you, alpha or the significance level is nothing but the type 1 error. So, it is easier to specify that than specifying type 2 error, and I should also mention that these type 1 and type 2 errors are not so friendly with each other. If you please type 1 error, the other one actually gets upset. So, you can think of this as a mother and daughter in law story or mother and wife story. Okay. where you try to please type 1 error, you try to lower that and then type 2 error shoots up, and vice versa. If you try to lower type 2 error, that is you design your test in such a way, hypothesis test in such a way, then type 1 error shoots up. So, that is also called a waterbed effect in many textbooks. Okay. So, the fact is that you have to specify one of these two errors, and usually it is a common practice to specify the alpha risk, and that is what we will also do. And very quickly we will see that this alpha that we specify in the hypothesis test is related to the level of confidence or the degree of confidence that we speak of in the confidence interval. We will come to that very soon. I also would like to give you a graphical understanding of a very common hypothesis test. In fact, this is the first corresponds to the first example that we discussed, where we are testing the mean of something, of a random variable, is some postulated value as against being not. So, for example, in this case h naught would be mu equals mu naught for some random variable as against the alternative. So, maybe I will just write it here because. So, h naught is mu equals mu naught as against the alternative mu is not equal to mu naught. We call this as a two-tailed test. So, what am I showing you here? What is this sketch, this graph that I am showing you here? The graph that I am showing you here is the distribution of a statistic that we are going to use to conduct the hypothesis test. I will just show you the graphs for different scenarios, then I will have a discussion on this once we go through the procedure for hypothesis testing. On the other hand, you have two other scenarios, right. So, when I am looking at the first example where the mean of a random variable is what is being put to test, the three possibilities are shown here. The first is all these three correspond to different alternatives, the null is the same in all. The null is that mu equals mu naught, this is the null. The first corresponds to the alternative is not equal to mu naught. That means there are two possibilities, mu is either greater than mu naught or less than mu naught, and that is why you have kind of a two rejection regions marked in red. We will come to that very soon. This is also known as a two-tailed test. The nomenclature becomes a bit more obvious once we understand the procedure for hypothesis testing. The second one corresponds to two different alternatives. One is that mu is greater than mu naught, and the other one corresponds to mu less than mu naught. Okay. These are the alternatives for which the graphs are being shown, and they are called respectively the lower tail test and the upper tail test. Okay. We will come to that very soon. Let us go back and now review the standard procedure or the typical procedure that is followed in a hypothesis test, right. Okay. So, what is the first step in the hypothesis testing? The first step is to formulate the null hypothesis. We will go through a couple of examples later on, so it will become very clear. Based on the postulate or the claim that has been given in the statement, accordingly you will have to choose an appropriate alternate hypothesis. For example, if I say that the mean of, I want to test whether the mean of a random variable is 0, then the null hypothesis in that case would become mu equals 0 as against the alternative mu is not equal to 0. But in many situations I may want to test if the average of a random variable is greater than 0. In that case also the null is actually mu equals 0, but the alternative is mu is greater than 0. Now, at this point of course people get into some confusion. Why is it that you want to test if mu is greater than 0, but your null is still mu equals 0? There are reasons for that, and these reasons are elaborated more clearly in the 12-hour video lectures that I keep talking about. But let me tell you quickly that the null hypothesis is always of the type of equality, and the alternative depends on what you want to test. But earlier I had said together the null and the alternate span all possibilities. But if you look at this scenario, you will find many such tests, mu is greater than 0. When you look at the combination of the null and alternate, they seem to not span all possibilities for mu, because there is yet another possibility mu is less than 0. Why is it that they do not span and yet people claim that the null and alternate together span the entire possibilities? Strictly speaking, when I want to test mu is greater than 0, the null actually becomes mu less than or equal to 0. That is strictly the null hypothesis, and the alternate is mu is greater than 0. But for a few reasons we remove that inequality and we place equality. So, it should be a habit for beginners to write the null and alternate as given by the statement, so that the null and alternate span the all the possibilities, and then take out the inequality if there is an inequality in the null and replace with a equality. One of the reasons why we want equality is when we conduct the hypothesis test, remember the status quo is the null and we are searching for evidence in the data to pull us away from the null, alright. So, what we do qualitatively in a hypothesis test is we assume, it is a conditional one, we assume that the null holds and search for evidence in the data to pull us away from that. And it becomes difficult to deal with the test if we assume an inequality for the null hypothesis. I mean, I am just giving you one of the reasons, this is not the exact reason, but this is close enough for you for us right now, that typical the general procedure for hypothesis test is you assume that the null is true and ask, when the null is true, how is it possible to have a data set that I have with me, or is it possible to have the evidence that I have with me. So, for example, you found a person coming in wet from outside into the room. Let us say you want to test the null that it is raining outside against the alternative it is not raining. There is no less rain and more rain and so on, here the alternate is not raining. Now, you ask in the only data that you have is this person has come fully wet, and let us say you are not seeing outside what is happening, you do not have any other data with you. Then you ask if the null holds, that is if it is indeed raining, what is the possibility that someone is coming from outside and gets drenched? It is quite high, right. So, therefore, there is not enough evidence to reject the null hypothesis unless you have some other data with you. You look outside or you see this person coming with an umbrella, then you say, well, I see the person is wet and has an umbrella. Now, when it is raining outside, then you ask how possible it is that it is raining outside and a person carrying an umbrella gets fully drenched. Then you may think, no, not so high. So, this person is drenched for some other reason, you may reject the null. Okay. So, in this discussion, remember, we have always held on to the null and asked, is the data now commensurate with the null? That is a simple thing, the null hypothesis. Typically, people get very intimidated or they get frightened at the hear of the phrase hypothesis testing, but it is a very simple idea. And the first barrier is usually setting up the null and alternate. Hopefully, this discussion has eased that for you. Right. So, the next step is of course choosing an appropriate statistic. So, when you are conducting a hypothesis test, think of yourself as a detective, and that you are going around with a magnifying lens in search of evidence to see if the null holds or if the null can be rejected. So, the statistic for the analyst or for the detective is the lens that you are carrying. The statistic is constructed from the data. When you look at the data, you may not actually be able to gather or see the evidence visually, but when you perform certain operation on the data, then the evidence comes out more vividly, either in favor of null or against the null. So, you can think of the statistic as a lens that or as some operation that extracts evidence that you are looking for, and here the statistic is a mathematical tool that works on the data. In fact, that is the definition of a statistic. It is some mathematical function of the data, extracts the evidence for you, and it could be a nonlinear operation, it could be a linear operation, depends on the statistic. How do I know which statistic to choose and so on? Is there are certain principles in choosing the statistic. It should be an unbiased estimate for give you an unbiased estimate of what you are searching for, that is a minimum criterion. It should be efficient, meaning it should give you the evidence with the least possible error and so on. Alright. So, the statistic is typically determined from the given problem statement. Suppose you are testing mean, then one statistic is a sample mean. Statistic you can read as an estimate, but we will use the term statistic. I could use sample mean, I could also use sample median. Both are unbiased, but the difference is sample mean is more efficient under certain conditions and maybe sample median is not. But if I know that the data has outliers, I may want to use a robust statistic for hypothesis testing, then I may use sample median. Alright. So, hopefully you have some idea now of what a statistic is. Once you have chosen the statistic, then you have to compute it from the given data. That is a very simple operation, we will not spend time on that. We will denote that by this zeta naught. Zeta is a statistic symbolically, and then you make a decision. How do you make a decision? You construct an you compute the statistic and you ask, if the null were to hold, is this statistic likely? Obviously, you can only make a decision in a probabilistic sense and not in a deterministic sense. So, as a simple example, in R, you have R norm, R unif, these are all pseudo random number generators. Let us take R norm, and if you look up the help on R norm, it says it generates random numbers or it allows you to draw randomly numbers from a Gaussian distribution with 0 mean and unit variance. Let us focus only on the mean. So, claim is that it is coming from a 0 mean process. How do you test if this is true? How do you test if R wrote this part of the claim? How do you test if it is correct? What do you do? Very simple, you generate numbers maybe of sample size 100, and now this is the data that you have, and now you have to test, right. Now you have to test using this 100 data points whether the claim of R norm is correct or not. What is the claim? The mean is 0. So, what do? You compute, you estimate the mean, that is what we mean by statistic. You can choose sample mean or sample median. Let us say you choose sample mean and you got some value. You can try this as I am speaking, you can open up R and you can do this, just generate 100 numbers, then compute the sample mean. Let us say you get minus 0.034. Now, what is your conclusion? That is, what is your decision? Minus 0.034 obviously is not 0, and that is expected because this is mean of a sample, whereas the 0 mean is for the population. So, looking at this minus 0.034, what can I say about the population, especially with respect to mean is the hypothesis test. Against the alternative it is not. I do not care whether it mean is less than 0 or not, greater than 0, I am only worried if it is 0 or not. So, the alternative in that case is mu is not equal to 0. You have 100 data points, the sample mean is minus 0.034. How are you going to now figure out if you should hold on to the null or reject it, right? We will do that, we will work out a similar example, but we will put it in a more physical context, and then you can apply the same to your R norm and check whether you hold on to the null or not, and depending on that you can start worrying about using R norm or not. Okay. So, such is the typical procedure. So, when you make a decision, that is the fourth step, which is the most important thing, you compare the observed statistic with some critical value. In fact, there are three ways of now making a decision from the data. The critical value approach is one of them, I will talk about that and then we will come back to those graphs. So, one is a critical value approach. So, you going back to the previous example of random R norm, if I have minus 0.034, then I will ask if truly, if I assume that what the people who wrote R norm, their claims are correct, then I ask is minus 0.034 a highly likely value or a less likely value. Or you say, well, I am going to say if I accept their claim, I am going to stick to their claim, I am not reject it, provided whenever I draw 100 samples, 100 observations from this distribution, I should not get a sample mean greater than some value in magnitude. It could be either positive or negative, that is what we mean by two-tailed test, right. You can say that I am going to tolerate sample means up to plus or minus 0.03. Whenever I draw a sample size of 100, you have to keep adjusting that critical value with the sample size, and that is what exactly is a two-tailed test, right. So, your rejection region is essentially two-sided. If the observed statistic falls below these two thresholds, then you reject, if the observed statistic. Now, of course, this requires the knowledge of what we call as a distribution of the statistic, that is distribution of sample mean. What are all the possibilities for the sample mean? Then only I can decide if I should choose the critical values in a symmetric way or in an asymmetric way to begin with. Secondly, I will know based on the distribution how to choose these critical values. We are not going to pursue that approach here, but I am just giving you an idea. Now, you can understand, you can try to explain to yourself in a lower tail test and in an upper tail test why the rejection regions are here and here. Okay. So, I leave that to you as a simple homework. Now, explain to yourself based on this critical value idea why the rejection regions are here. In these graphs, by the way, I have assumed that the statistic that you are using follows a Gaussian distribution. Sample mean we know follows a Gaussian distribution. If it is not, if it is some other distribution, for example, sample variance follows a chi-square distribution, still this alternative will be a two-tailed test, but the rejection region is not symmetric. Okay? That is the only difference, but otherwise always the alternative of the types theta is not equal to theta naught will be called a two-tailed test, because the rejection regions are going to be on both sides of the postulated value, and the other ones will be either lower or upper tail test. Okay. So, I will leave this discussion at that and get back to the different approaches. So, we have just discussed a critical value approach, where I decide what a critical value should be, which is usually done based on the distribution of the statistic and the alpha level. Together you will use that to determine the critical value. That is what you will see commonly in many hypothesis testing exercises. Then there exists something called a p-value method. Again, this is something which we are not going to spend time on, but the basic idea here is you look at the statistic and you ask what is the probability of obtaining a more extreme value than what you have obtained. So, suppose you had obtained sample mean as minus 0.034, you ask yourself what is the probability of obtaining, assuming the null to be holding. You have to hold on to the null, you have to hold on to some branch, you will hold on to the branch of null and ask what is the probability that if this is the branch I hold on to, these things are likely. So, here in the p-value method you hold on to the null and you ask what is the probability of obtaining a more extreme value. In the case of mean, we are asking what is the probability of obtaining a value less than minus 0.034 or greater than 0.034. You have to look at both sides in some sense. It is not exactly that, but more or less that. So, you will actually look at both possibilities and then sum up the probabilities in a two-tailed test. In a lower tail test you will look at the probability on one-sided probability, in an upper tail test also you will look at other one-sided probability. And depending on the probability that you get, that probability is called the p value. If the p value is less than the significance level, then you reject the null hypothesis. So, there is a nice saying in the book by Professor Ogunnaike, Babatunde Ogunnaike, whose reference is given at the end of this slide. If the p value is low, the null hypothesis must go. So, there is a nice rhyming to it, you can remember it. What we shall use is a confidence interval approach, and I will illustrate that with couple of examples. I find the confidence interval approach most easy and also intuitive. So, what you do is in confidence interval approach, as you must recall what a confidence interval is, we construct a confidence interval for the parameter that I am testing. If I am testing for mean, I construct confidence interval for mean. If I am testing for variability, I will construct the CI for variability and so on. But at what degree will I, what confidence level will I construct? 100 times 1 minus alpha percent. Typical values of alpha in hypothesis testing are 0.05 and 0.01. So, if alpha is 0.05, I will be constructing 95%, and if alpha is 0.01, so this is alpha 0.05, and if alpha is 0.01, the confidence level is 99%. So, depending on the value of alpha, I will construct a 100 times 1 minus alpha percent confidence interval, and then it is very simple. Look for the postulated value within the confidence interval. If you find the postulated value, which is, that is, this you are searching for the truth, and if the truth is contained in the confidence interval, then you say, well, the null hypothesis cannot be rejected. That means the postulated truth is indeed there in the data. If it is not, then you say the data comes from alternative hypothesis. So, essentially you are saying, let us assume that the null is the one that generated the data, search for the evidence in all these three. Is the evidence supportive of your null or not? Is that what you are asking? That is all.